Evan, would you like to say hi to Stuart? Hola, Stuart. Hola, Stuart. We hope you have a phenomenal weekend. We don't have most of the class here because they have something better to do called choir, chorale, and that's just fine. So, uh, today is a good day, you guys. The stuff that we talk about at the beginning of chapter 4 is stuff that you are 100% fully capable of doing. It's not as challenging as related rates, which you did a fine job with, and ultimately you're my guinea pig group. I hadn't done that for a while, and next year your efforts and your patience will pay off for the next group. So we want to talk about maximums and minimums, and we want to talk about absolute maximums and minimums, and then local maxes and mins. And I have a picture here, and we'll talk about that in a second. But first, absolute max and mins. Absolute max we're going to define as the largest value of a function over a given interval. So you could say, well, we want to know, the absolute maximum from, say negative infinity to positive infinity. Or you could say, I want to know from -2 to +5. You can include values, exclude values. So all those things apply. But it doesn't have to be from negative infinity to positive infinity. You can exclude certain values. Absolute minimum would be the smallest. We'll just use quotes. I did that one time. Some people said, what does that mean? So, well, that just means that, everything else from above carries down except for that first part, right? Local max. Local max we're going to define as this. Largest value relative to those around it. It's also referred to sometimes as a relative maximum. As you can see, absolute max and absolute mins are sometimes referred to as global maxes and global mins. It really depends on the book that you're using. Local minimum, again, would be the smallest. And so there's some new definitions, and you should be able to think about these things in your mind as you're moving forward. But calculus really helps us work with these. My pre-calculus class has been very frustrated because they've been graphing higher order polynomials, and when they do so, they say, Mr. Gens, how far down does it go? When you draw this part. And I said, well, you don't know. You won't know that until we do calculus. Well, you guys will be able to graph significantly difficult polynomials and be able to understand exactly how high and how low it goes. Calculus allows you to do that very efficiently. So looking at the graph provided, identify the absolute max, min, as well as the local max and min values. And what I try to do is I try to just start at one end and work my way over, and I pick out the endpoints, and I also pick out then, kind of what would you say, peaks and troughs? Peaks and troughs? We'll play the song on Monday, huh? Good times. All right. So I'm going to start here. I'm just going to write f of -3. What is f of -3? -27. And then I have another interesting point right here. I'm going to write f of -2 is what? -152. And then I have another interesting point at 1. F of 1 would be 37. I have another interesting point at f of 3. That is... No, f of 2 really isn't that interesting. But f of 3 is. What's f of 3? -27. And then f of 4 is 64. So what we want to do is, those are the interesting points. I'll show you why in a second. We want to identify which ones of those are absolute mins, absolute maxes, local mins, local maxes, and then which are neither possibly. So obviously, what's the smallest of all these? And negative 152. So this one right here is going to be our absolute min. Oh, maybe not. So, what's our absolute max? Yeah, at 4 we have a value of 64. So this would be our absolute max. Well, and then the definition of a local or relative min or max really depends on those points around it. So, you know, which points on here have are kind of it's a highest or lowest compared to those around it? Yeah, f of 1 is going to be a local max because this is the biggest point compared to those immediately around it. So we would call that f of 1 would be a local max. What else? F of 3 would be a local min. And technically, f of negative 2 is also a local min, isn't it? It's an absolute min. It's also a local min. So we can be both. Nope. You'll see some examples. Um, this point here is none of the above. Okay? It's none of the above. So really, as you think of it, in terms of being a local, it has to really be on both sides. And you don't have any values on this other side. So there's nothing really local about it. It is an endpoint. It is going to be extreme just by nature. So it could possibly be an absolute, but not local. So this guy by the name of Fermat, who's really famous and proved a theorem when I was in, no, somebody proved Fermat's last theorem. He lived back in the 1600s. He said something about calculus, which is very important, okay? And it says this: if f has a local max or a local min at C, and if f prime of C exists, f prime of C must exist, then f prime of C is equal to 0. Now, there's a whole lot of mathematical language like that I could have used previously, and I didn't. If you were to be a math major, you would have to learn all that and learn it very, very, very well. But I think that this is a piece that we do want to see. And what is primarily saying this, what does this piece mean here? Well, what does this piece first mean? F prime of C exists. What does that mean? That there's a slope at that point, that there's a derivative at that point. Why wouldn't there be a derivative at a certain point? What kinds of things don't have derivatives at certain points? Okay, vertical, undefined, stuff like that. So first of all, the derivative must exist. And then what does this mean? Slope is 0, a horizontal line, right? So if you were to look at these right up here, I just want you to just draw a nice sketch. This point right here, if we were to draw the tangent line, the slope is 0. So you can see that this is a local min. The tangent line has a slope of 0. Same thing here, slope of 0. Same thing here, slope of 0. So wherever the derivative is equal to 0, something very interesting happens. And that is very valuable information to us. We're going to use that for the remainder of chapter 4. Okay? Here's another piece. Critical numbers are things we like to kind of examine. And a critical number of a function f is a number c in the domain such that either f prime of c equals 0 or f prime of c does not exist. So as Fermat just talked about, he said that, those are local max and mins, we need to make sure that these things fall into place. Well, we like in calculus, we like to check to see where the derivative is equal to 0 and where the derivative does not exist. Those points are very interesting to us. So let's look at examples of critical points. If you see a min or a max, like right here, this point right here we would call a critical point. And this point right here we would call a critical point, namely because the derivative is equal to 0. And if I draw another graph that looks like this point right here is a critical point because the function is undefined at that spot, and therefore the derivative would be undefined as well. So that's a point we have to take into account. If you have a corner of a graph, let's say an absolute value function, we would call this a critical point that we need to check out. That one's important. And then if you have a vertical tangent line, such as a graph that looks like this, which we kind of come to know, that spot right there as well refers to a critical point. So those are points we have to be capable of finding. Graphically, it's easy to identify them. Algebraically, it might be a little bit more difficult. So using your graphic calculator in incorporation with your algebra, you'll be able to do it pretty well. So why don't you take out your graphing calculator. I'm going to orient this. It's a little off. My baby girl turns 1 year old today. Tenley is 1 year old. She's not going to come to a basketball game. She's going to have her first taste of cake. In fact, Tenley at 1 year old, she's never even actually had something very sweet like candy or a cookie. No. Yep, she is sheltered. Sheltered with my love and care, Taylor Blake. Yeah, take that. Take that, Taylor Blake. So there's a boys basketball game tonight. There's a hockey game tonight. No. Wrestling meet tonight? All right. That's my wife used to teach in Farmington. She was a biology and chemistry teacher in Farmington. I once chaperoned a prom at Farmington. Yeah. Yeah. Good times. Good times at Farmington High. Okay. So, in order to find critical numbers, what we have to do is we have to look at our definition. And it says in order for critical numbers to exist, that happens either where f prime of c is equal to 0 or where f prime of c does not exist. Well, I'll tell you this right now. If the function isn't defined at a specific point, we already know that the derivative isn't going to be defined there either. So that's one thing we can look at. Is there any point where the current function for a is not defined? No, you can plug in any number there, you're going to get a number out. So what we need to do is take the derivative and set it equal to 0. So f prime of x is equal to what? 3x squared minus 4x plus 1. We set it equal to 0, and we solve. Any factoring geniuses here? Very good. -1 and -1. That will work out. And so what would x be in that situation? 1/3 and 1. So you have critical points or critical numbers at x equals 1/3 and at 1. If you graph that on your calculator, let's actually try that. We'll just do one of these. Let's take out your calculator and y equals x to the third minus 2x squared plus x. And I'm going to change my window to something a little bit better. I'm going to go from -3 to +3 for x. I'm going to leave the y alone. But I think if I change my x values there, I should probably get a better look at it. Girls basketball tonight? Where at? Oh, Casson, Manderville. My wife's from Casson. Oh, gosh. Oh, wow. No. Wait a minute, what's going on here? I don't really see much happening there, but it says something's supposed to happen at 1/3 and at 1. Maybe if I decrease my y values, let's put our y values at -1 and at +1. And then if I graph it now, there we go. See? So that tells me that there are interesting things that happen at 1/3 and at 1. In fact, I have a local maximum and a local minimum. So we can define those ahead of time. Okay? X squared minus 1 over x. Is there a spot where that function is not defined? 0. So we already know that 0 is going to be a critical number or a critical point. We know that one because you can't have 0 in the denominator. So in order to find the other one, I have to take the derivative and set it equal to 0. How do I take the derivative of this? Quotient rule. F prime of x is equal to the derivative of the top, which is 2x times the bottom left alone, x, minus the top left alone, x squared minus 1 times the derivative of the bottom. What's the derivative of the bottom? 1. Divided by the bottom squared. So in other words, f prime of x is equal to 2x squared minus x squared, which is just x squared. And then minus the -1 would be plus 1 over x squared. So the derivative is x squared plus 1 over x squared. Where is that derivative undefined? 0. The derivative is not defined at 0, which is the point that we already know we have. But where the derivative is actually equal to 0 would be where the top equals 0. So we need to know where x squared plus 1 is equal to 0. X squared plus 1 equals 0. Subtract 1. X squared equals -1. Square root both sides, and you get x is equal to plus or minus I. What does that mean? There's nowhere that the derivative is ever equal to 0. So you don't have a local max or min. If you were to graph this, I promise you, you will not see a local max or min. This graph looks something similar to, say, that. It doesn't have a local max or min. And it's possible for graphs to have it. So we learn about the nature there. So our one critical point is equal to 0 because that is where we have our vertical asymptote where our function is undefined. Am I about right, Bryce? Okay. So it has a little slant to it, looks like. Okay, so if you graph it, it'll be something like that. C. I have 3x minus 6. Absolute value of 3x minus 6. Do you know what that graph looks like? Yeah, it looks like a V, doesn't it? And something interesting happens when this changes from positive to negative, or where it happens at 0. So I'm just going to take this thing and set it equal to 0. I'm not even going to take the derivative, because I know about this function. Is there ever a time where the slope of this is equal to 0? No, there isn't. But I have a point where I can't take the derivative. It's going to be at that point, which is going to be when this portion is equal to 0, or 6 equals 3x, or x is equal to 2. So 2 is the critical point in that situation. Does that make sense? So I didn't even take the derivative here. If you know that it's not going to happen, then don't worry about it. In order to take the derivative, we have to look at, the negative portion and the positive portion. We don't need to do all that. Okay, the last one. This is a good one. It makes sure that we understand a little bit about fractional expressions, things like that. I have square root of x to the third. How do I rewrite that? X to the 2/3, very good. Or 3/2. X to the 3/2. Minus 2x to the 1/2. Okay, so now I can take the derivative of it. Before I got confused, and I don't like getting confused. So what's the derivative of this thing? F prime of x is equal to what? Very good. 3/2 x to the 1/2 minus x to the -1/2. Good. Are there any questions where I got that? That's my derivative. Now, It would be helpful if you wrote it without negative exponents. F prime of x is equal to, looks like we got 3 square roots of x over 2 minus 1 over the square root of x. Well, where's the derivative going to be undefined? Can't have 0 in the denominator. And you got a square root of x in the denominator, so you know one critical point is going to be 0. So critical point equals 0, that's going to be 1. The rest of it is a little bit more difficult. I would have to set this thing equal to 0 and solve, right? It's not that bad. If I want to take this minus this and set it equal to 0, I'm going to use a little trick here. I'm going to I'm going to add my 1 over the square root of x over the other side. I'm going to cross multiply. So I'm going to go 3 square roots of x over 2 equals 1 over the square root of x. And then I'll cross multiply there. So I get 2 times 1 is 2 equals, what's 3 square roots of x times the square root of x? 3x. In order to solve for x, divide both sides by 3. So I get x is equal to 2/3. Now, we really should check that because when we cross multiplied, we may have created a solution. How would I check to see if that point could actually be there? What would I do? Yeah, you could plug it in. What else could you do? You could look at the graph. And when you look at the graph, if you get a local minimum at 2/3 or a local max, then you know you probably did it correctly. But because we cross multiplied, we might have created a solution there. So that's one thing we can do. Let's check it really quick. Square root of x to the third minus 2 square roots of x. So we graph it. Oh, what do you notice? Sure enough, at 2/3, I have a local minimum that exists. That was valuable information. And we found that by doing all that. That's a critical point as well. At 0, something happens. It actually, in this case, it ends up being that's where the derivative is not defined. So that's a point where you probably have a vertical asymptote possibly, or the function goes vertical. So we would have to check that if we were going to find max and mins and things like that. So one more piece here, closed interval method. Here's what we want to do. In order to find absolute min and max on a closed interval, first of all, what we first do is we find, find where f prime of c is equal to 0. So we've talked about local max and local min and critical points right now. But what about finding those absolutes? Well, first thing, you got to check to see where the derivative is equal to 0. And on our previous page, that would give us these spots right here. But how about those? What do we do for those? Those we have to check our endpoints. Check endpoints. And third of all, compare results. So we have this graph, x squared minus 4x plus 3. What shape is that going to be? It's going to be a parabola, and we want to find the absolute maximum, minimum over the given interval, 0 to 6. So the first thing I do is I look for local min or local max and see what that would be. In order to find that, I do f prime of x equals what? 2x minus 4. And I set that equal to 0 and solve it, right? Set equals 0, what's x equal to? 2. Now, that tells us the location. That doesn't tell us the actual height. If I wanted to find out the height, what would I do? Plug it in. 2 squared is minus 8 is negative 4 plus 3 is negative 1. So I'm going to write it like this. I like to do this. F of 2 is negative 1. I like to write it like that. It tells me the location and the function value. Helps me kind of keep things straight. So I did the first part. Now I should check the endpoints. I need to find where the height of the function is at 0 and where the height of the function is at 6. F of 0 is what? 3. F of 6 is what? If we plug it in, 6 squared is 36, minus 24 is 12, plus 3 is 15. So if we were to graph this, we actually have a really good idea what the graph would look like if this is 6 and this is 0. At 0, the graph is up here at 3. Then it's down at 1. And it goes way up to 15. So that's the portion of the graph that we're looking at. So we should be able to think in our minds what's kind of happening, okay? So you tell me. It says find the absolute max and absolute min. What would be the absolute max in this situation? Right. 15 is max. Whoop. Should probably write absolute. And what's the absolute min? Negative 1. And you do that same process. You would check to see where the derivative is equal to 0. That will give you this point right here, and then you check the endpoints to see where they are over there. And notice that our local min also was an absolute min, and then one of our endpoints was a max. So we can let the other one go. I think you guys have you get that, right? I don't think we need to exhaust with another problem. We can maybe do that one on Monday. So I'll stop here. Goodbye, Stuart. Hope you have a good weekend.